Okay. All right, today we are very happy to have Alejandro Morales from the University of Massachusetts at Amherst, and he's going to be talking about refinements and symmetries for volumes of flow polytopes.
Thank you very much, Eric. Thank you, Sandra. Thank you for the invitation. It's great to speak in the seminar. This is a joint work with William Shi, a student I worked with through and the MIT Primes program, and the beginning is also have some work with Carolina Benedetti, Chris Hanusa, who is a local, Pamela Harris, and Anthony Simpson. Okay. Okay, so Ron Graham passed away this summer, and he was a great combinatorialist, computer scientist, and he did also great work for the mathematical community. And also he was a great juggler. So I thought, I should, with this quarantine, and I should kind of pick up on an activity, and I thought juggling would be a good one. So I got this book, this really beautiful book he has with Percy Diaconis. When there's magic, but also has a chapter on juggling, and they start with describing the mathematics of juggling, and then they go and actually show you how to juggle. And this is one of the pictures of the steps to juggle. So let's start with a little bit of the math of juggling. So a juggling sequence is a sequence of arcs specifying the amount of time a ball is thrown. So here is a picture of Ron doing the 3-ball cascade. So here you would throw a ball so it lands on height 3, and then you would kind of repeat this pattern, until you stop. But let's say that we stop at this time here. So that would be a 3-ball cascade. So you see, you kind of throw a height so it lands at time 4, and time is discrete. Okay, and then you could have, hi Chris, I see. And you could have, you could have like left. You could put like the hands left and right, left and right. That's not going to be so important for us, so we could assume it's one hand. Is this clear how this is being represented? But this is a kind of one juggling sequence. But even in that book, it tells you that if you're trying to learn how to juggle, you should start just with one ball. So let's maybe simplify this, and let's now maybe ask more mathematical question: in how many ways can we juggle one ball with time n? So let me do the first one with time n equals 1. I can only throw a ball to time 1. So maybe, I don't know if you can see this in my camera, but if you have, it would just be 1. But how many ways can you do it with time 2? So what do people think? Maybe let me check the chat. Or you can speak up and maybe tell me the different ways of doing this. So I'll do 1. So you could do 1, 2. So that corresponds to this. And maybe, okay. Is there another way of doing it?
So you could throw the ball up, so it takes 2 seconds to come
exactly
down?
Right. So you could do 1, 2. Okay, great. So there's 2 ways. And how about with time 3? So let me do kind of this one, and I'll do the version that Eric said, but now higher. So it could be 1, 2, 3. Okay. What else could you do?
So you could do like a 1 second and then a 2 second, right? Or the reverse.
Right, exactly. So I could do this. Thank you, or Megan, or you could do this. So, and that's it. So in total, there's 4. And in general, there's 2 to the n minus 1 ways to do this in time n. And maybe you can see a correspondence with subsets here. So is the question clear? And we see. Okay, good. So that's good. 1 ball is good. So maybe let's pick it up. Let's start adding balls. So let's call it J, S, and T. How many ways can we juggle T balls with time n? So let's try n equals 2, T equals 2. And here in gray, I have all the possible throws. So I can have a throw of time 1, or I could throw a ball of, so in gray, you see all the possible throws. Okay, and the balls are indistinguishable. So, maybe before, if you saw the connection to sets, maybe here you say, well, maybe there's 2 sets. You have maybe 1 ball here you could throw like this, and the other ball could be thrown. I said they're indistinguishable, but just so we can see. Okay, so maybe you have like sets that are nested. So how many do you expect here? So here, well, maybe you can draw all the possibilities. So you could have, oh, yeah, it's, I'm left-handed, so the sometimes software is yeah. So that's one, and you could have kind of both a long throw, and is that maybe it for this? So yeah, you either both throw. You can throw two balls high. You can throw them once, or mixed. So there's three. Okay, and with n equals 3 and t equals 2, how many do you expect? Maybe kind of. So before we had 2 to the n minus 1. Here we had, in this example, 3. How many would you expect? So maybe if you have this one set containing the other, maybe you could think of maybe it's 9. But there's actually, but that's not quite, there's not enough, because there's also this possibility where you have kind of crossing balls, I guess. But so there's also this configuration. Okay. So then in general, in total, you have 10. Okay, and the other 9 is where like one ball is below the other ball, kind of, or they're doing the same thing. Okay. Any questions or with clarifications?
Yeah, there's a question in the chat. So there's no restriction on balls not falling down at the same time.
There's no restriction. No, so I'm allowed to have maybe at a given time more balls in my hand, like 2, but but the time is discrete. Maybe does that answer the question? Maybe. Yeah, balls can land at the same time. You can at some point, like here, for example, in this situation here, at this stage, your hand received the 2 balls and threw them again. Okay.
I have another question. Say
yes.
for n equal 2, is it possible that one of the balls is not in the action? So say the case that one of the balls is actually thrown, but the second ball is thrown at time 1 rather than, so it kind of waits 1 second and thrown in the second half of the period.
So in this model, I wouldn't allow this. Yeah, so you have to kind of handle the balls. You cannot. I guess if you keep something, is like if you throw it at height 1, kind of. Yeah. So.
So they have to be in action all the time.
They have to be in action. Yes. In this model. Yeah. Thank you. Yeah.
Mm-hmm.
So. Yeah. So here, I guess we had 3. Here we had. Yeah. So here we had 3. Here we had 10. Let me repeat that. But in general, there's no nice formula for this. If you have more than, as a function of n and t. So here are maybe some bounds. So if you think of the sets kind of nested, if you kind of count tuples of sets that are kind of contained in each other, you get t plus 1 to the n minus 1, but that's not all of them. So that explains the 9 that are here, but we saw one more. And the upper bound, the best one I know is this one. Okay, and this is from work with Carola Mesaros, who is, I guess, in New York, in Cornell, and Jessica Stryker. So, and this connection, this was obtained through alternating sign matrices. So it kind of it's a bit non-trivial. So if you can improve these bounds, that would be great. But kind of okay. So then somehow even this problem is kind of hard. So let's maybe go back to learning how to juggle. So later in the book, they say that to begin juggling, it's necessary to have some reasonable objects to juggle. Some jugglers fill tennis balls with sand or some kind of grain to make them heavier. So I guess when we read this, we could think, well, maybe what if we try to juggle sand? What if we kind of our balls can disintegrate and we can juggle fractions of balls. So for example, you could have your ball could break into 1/2, 1/2, and then this hand you could throw, say, 1/2 here, and then here you could throw 1/2 here. Okay, so now the balls don't have to remain complete. Is it clear what I'm considering now? So another possibility could be 1/4, 1/4, 1/2. So you throw a fourth of the ball, height 2, fourth of the ball, height 3, half of the ball, height 2. And here, this could distribute like this. Okay, so so you start with one ball, it kind of disintegrates, it propagates, and then at the end you get back your ball. Yeah, so is that clear, that generalization?
So the only condition is that the incoming edges and the outgoing edges, the sums have to be the same, right?
Right, the balls, everything is in action, kind of, even in this end, yeah, and we'll talk more about that. So with the generalization, we cannot. So let me just do the other one here. You cannot count them because of the real, but you can say, well, what's the set of these sand juggling sequences with one ball in time n? And the answer, it's a polytope. So in this case, we actually get a simplex. So the vertices here are those 4 balls, like when you throw like in balls entirely, one ball entirely, but then the set is actually a simplex. So here maybe it's a good opportunity to review what a polytope is. So a polytope in Rn with integral vertices, so the vertices of integer coordinates, you can think of it as the convex hull of finitely many of these vertices, or the intersection of finitely many half spaces. Okay, so let's look at the example of the hypercube. You could think of it as the vertices could be the all binary sequences of size d. Or if you think of it the half space description, you could think of it as d real coordinates going between 0 and 1. So that's the intersection of your half spaces. Okay, so you have this one here, the one below, and so on. Okay, so these are the 2 ways to think of polytopes. So let's now go back to our sand juggling. So as Eric was pointing out here, in every possible throw, I have a variable. So everything has to be negative. And say for the first, at time 0, well, whatever you throw on height 1, whatever you throw on height 2, and whatever you throw on height 3, that better be equal to 1. The one ball you start with. And then say at this time here, whatever you throw on the second time on height 1, whatever you throw on height 4, better be equal to what you receive from here. Okay, so basically you can only juggle what you received at this point. Yeah, and now let's focus now on this time slot. So whatever you throw on height 1 here should be what you receive from here. Okay, and at the end, at the very end, the ball has to kind of reconstitute itself. So x14 plus x24 plus x34 better be equal to 1. And then this is the half space description of a polytope. So that's why it's a polytope. Okay. Any questions with this? Okay. So that's why it's a polytope. And now we could kind of maybe stop talking about sand juggling and focus now on so these polytopes are called flows because you could think of these quantities as being kind of flows on edges. And we can do it in more generality. We can start with a cyclic connected graph G with n+1 vertices and m edges. And you can now a flow polytope is an assignment of a non-negative real number in each edge, so that the net flow vertex at a given vertex is AI, which is part of our input. But mostly we're going to care at when our net flow is 1, 0, 0, 0, minus 1. So you have 1 unit of flow in your source. You have the flow is conserved in the middle, and you have 1 unit of flow in your sink. Okay, and so now this is this is a flow polytope, and the example of this like one ball, this one ball when we do the sand juggling is the case when we have the complete graph K4, because we're allowing every possible throw. Okay, any questions? Okay, and then as I said, for this complete graph of 4 vertices, we get a simplex here. Okay. Okay, good. And these flow polytopes are have been actively studied. They have connections to other parts of combinatorics and math. So there's some early work in the 2000s relating to toric geometry. Some more beautiful work of Baldoni and Michel Vergne related to Jeffrey-Caron residues. There's some relations to cluster algebras. There's connections to diagonal harmonics in algebraic combinatorics, to some other important families of polytopes like generalized permutahedra. There's been work relating them to Schubert polynomials. With different graphs, you get relations to Gauss and Zetlin polytopes and kind of tableau and Schur functions. And there's relations to associahedra and permutahedra, some very nice work of Martha Yip, Rafael González de León, upcoming work, Von Bell and Mayorga and Bernard and McConville. They've been connected to some hyperplane arrangements, and this connection you saw from juggling sequences was some recent work with Carolina Benedetti, Chris Anusa, Pamela Harris, and Simpson, who was a student at Williams. They're related to rational Catalan combinatorics, and we have this group so that's the name. So here the H is Hanusa, Pamela Harris, Benedetti, González de León, and Martha Yip. And they're related also to, as I mentioned before, to alternating symmetrices, and so they're actively studied. I guess that's what I'm trying to say. Okay, but let's go to the more balls maybe. So remember that JS and T was the number of ways of juggling T balls with time n. So say that you have n equals 3 and T equals 2. Well, you could think of that as, in terms of the flow polytope, you could think of it as, well, that means I start with 2 balls. The balls have to be conserved in between, and at the end I have -2. Okay, so here you're really just talking about, it's still a flow polytope, but at net flow 2, 0, 0, -2. But if you just care about in how many ways you can juggle balls, here the balls are not allowed to disintegrate. They have to be, so what you're doing is you're looking at the lattice points. So in this case you have 6. So you're counting. So if you're looking at this, is basically the number of lattice points of this polytope where your net flow now is 2, 0, 0, -2. And in general, T 0, 0, -T. Is that clear? Yeah. Okay. So if you're interested in this, actually it's related to this problem of juggling more balls. It's actually related to this like sand juggling. It's just counting lattice points. Okay. And then moreover, if your net flow, instead of being 1, 0, 0, -1 is T 0, 0, -T, this is the same as take the polytope at 1, 0, 0, 0, -1 and stretch it, dilate it by T. So it's actually just related to the one juggling one ball, like with one sand ball. Okay, so let's recall maybe a little bit of this lattice points. What are lattice points of polytopes? Or are any questions with this? Okay, so in some sense, juggling more balls is intimately related to this sand or juggling or this real juggling. Okay, and here you just look at the lattice points. So so the number of lattice points of a polytope is sometimes called the discrete volume. So for example, this simplex here has 3 lattice points. And if we look at the function that counts how many lattice points, you take this polytope, you dilate it by T, and you count the number of lattice points as a function of T. That's a known function, and it was studied by a French, I think at the time, I think he was a high school math teacher, Erhard, and it's called the Erhard polynomial. So when your vertices are integral, you actually get a polynomial function in T. So for example, for the simplex, if you dilate the simplex, the only thing that's changing is, well, now this is a T. And now if you count how many lattice points you have, well, you're asking, well, how many integer solutions do I have of this equation? And this is kind of a counting bars and dots counting problem. So it's just given by a binomial coefficient. Okay, how many tuples add up to t, or up less than or equal to t? So you can see, at least in this very example, that indeed you get a polynomial in t. Okay. Okay, so so let's go back to our flow polytope. So the number of lattice points of a flow polytope is sometimes it's called kg. I mean, this is just kind of the value of the Ehrhart function at 1, where you just don't dilate the polytope. So this is called k because for the capital K, because when you take the complete graph, which confusingly is also little k for us, so we don't get too confused, it's called Costant's partition function. So Bertram Costant was a representation theorist, and he was interested, he studied this function. So so let me remind you that what you're doing here is counting integer flows. So for example, for this case, you have k3 and 1, 0, minus 1. How many integer flows are there? Well, if you're distributing a ball, you can just do this, or you could, and this is 0, or you could do 1 and 0, 0. And this was the example from the beginning where you either throw a ball like this, or you throw a ball like that. So here, there are only 2 lattice points. So I would say that the constant partition function of my K3 at 1, 0, minus 1 is 2, the number of integer flows. Okay? Yeah. Okay. And when you're counting integer flows, you the generating function of this number of integer flows, of this constant partition function, has a product formula, has a so let me explain this. Well, you might recognize here that you have like a geometric series, because let's think of an edge, okay? So that if that edge has an integer flow n, it's going to contribute n to the ith vertex, and it's going to subtract, it's going to remove, it's going to be negative flow on the incoming jth vertex. So you would encode that with xi to the n, xj to the minus n on this side. And now, if you're doing a generating function, each edge is independent. So you would add over all n bigger than or equal 0, and this would become the geometric series. Okay? And you do that for each edge, so you get a product. Okay? So if you're successful in extracting coefficients here, you can compute the number of integer flows, the number of lattice points, and so on. But that's kind of, it's hard to extract, but in principle, it's encoded there. Okay? And so maybe I jumped a little bit the gun here, but the reason Costant studied this is because there are formulas for in algebra of weight multiplicities and tensor product multiplicities in terms of this this function. And maybe like in type A, sometimes people call this Koska coefficients. They count semi-standard tableau that you might have heard. And tensor product multiplicities are examples of that are the Littlewood-Richardson coefficients that you might have seen if you studied symmetric functions. Well, anyways, so these, just again, these things are of interest. Okay, but let's go back to juggling.
Wait, Alejandro, there was a question in the chat. Why are the edges independent? Chris.
Oh, right. I mean, so because you're summing over all possible net flows. So I mean, when you fix A, the edges are going to be dependent. But if you're considering all possible net flows you could get, then it's because we're summing over all A. That's to answer your question. Okay. Does that?
Well, I think that can help. But
yeah. Thank you. Oh yeah. Right. Maybe that's yeah. So it's because here is a generating function. So we're summing over all A. So we're not focusing on 1, 0, 0, minus 1 or anything, but considering all of them. Thank you. But yeah, maybe that. Yeah, but yeah, it's important because I'll talk about the generating function a bit later. So that's good to clarify.
Okay, thanks, Alejandro.
Thank you. But remember that somehow, even for the complete graph, this is the number of juggling sequences of t balls time n. So this is the same as that we said before. This is the same as the number of lattice points of this flow polytope. Okay, but even this is difficult, right? So this is so there's no nice formula for that. So so I guess the conclusion here is that the discrete volume, which is the number of lattice points, is hard. Okay. So and yeah. Okay. So and this is basically this is the number of lattice points of take the original flow polytope at 1, 0, 0, minus 1, dilated by t, and count the number of edges. Okay. So if the discrete volume is hard, why don't we look at the Euclidean volume? Oh. So the continuous volume is the Euclidean volume. And in combinatorics, it's better to look at enumerative combinatorics. It's better to look at the normalized volume, where you take the Euclidean volume and you scale it by the dimension factorial. And the reason for that is that you obtain a non-negative integer if your vertices are integral, like anything here. And we like non-negative integers; they count things. So for example, in the simplex here are the simplices. The Euclidean volume here would be 1, 1/2. Here is 1/6. But the normalized volume you scale by the dimension factorial would be just 1, 1, 1. So the simplex is like the building block. So when you've heard of triangulating a polytope. So when you triangulate a polytope, you're able to calculate the volume because each simplex has volume 1. Okay, so let's take the flow polytope of the complete graph. This is the kind of the sand juggling, one ball. So this flow polytope is actually called the Chan Robbins Yuen polytope. So we summarize it by Cry. So it was kind of studied. It was studied in the 90s by Clara Chan, David Robbins, and David Yuen. And here is the table of the normalized volume. So if you maybe have not seen this before, do you see anything? You can put on the chat. Do you see anything with these numbers? Do you notice something about these numbers? Anything particular, maybe? So something interesting is, well, maybe is 2 divides 10 and 10 divides 140. And maybe you could try further, and 140 actually divides 5,880. So maybe if you probably, since you're in computers, you probably have access to the computer calculators. Maybe you could help me write the quotients. Okay, so 2 divided 1 is 2, 10 divided 2 is 5, 140 divided 10 is 14. Did anyone get the answer of 5,880 divided by 140?
42.
42. Okay, thank you, Eric. Thank you. So you get these numbers, and let's divide 1 by 1. And this is a very famous sequence of numbers. They are the Catalan numbers. So here the sequence we got was, okay, so the normalized volume, which from now on I'm going to call the volume of this polytope, is the product of consecutive Catalan numbers. And this was proved by Zeilberger in 1999. So the Catalan numbers, the sequence here, count more than 200 objects, like, for example, triangulations of an n-gon, dig paths, or plane trees, and many, many more. And this is collected in this beautiful monograph of Richard Stanley that used to be, well, it is also a part of, inspired by maybe the biggest exercise in any textbook, in his book Enumerative Combinatorics. So they have more than 200 different interpretations, but there is no combinatorial proof of why the Catalan numbers are appearing here. And this is just it's been a big mystery. So that's kind of motivating for the rest of the talk. So an outline maybe, maybe with juggling and so on, I told you what a flow polytope is. And I said that the volumes and lattice points are important in combinatorics, but also in other fields. And then this particular case of just this real juggling of one ball gives this beautiful volume formula that's the product of Catalan. So now let me tell you a little bit about the proof, but any questions? Okay, so about the proof, remember that kg is the number of lattice points of the flow polytope, or the number of integer flows. So there is this theorem that I like to call the fundamental theorem of volumes of flow polytope, says this result of Stanley and Posnikov and Baldoni and Vergne, that says that the volume of a flow polytope at net flow 1, 0, 0, minus 1 is given by the number of lattice points of a very similar polytope. So you keep the same graph, but now your input is these numbers ij, which are just the in degrees minus 1. So it's a very surprising result, because it's telling you that the Euclidean volume equals the discrete volume. So that's interesting. So let's do an example. So here's a graph G, and here's the flow polytope. Okay, so let's compute its volume with this result. So it says, well, if you compute the volume, you should count integer flows with in degrees -1. So let's calculate the in degree -1 here. Okay, so, and I guess the first one is supposed to be 0, so this should be 0. And now can you tell me what is the in degree -1 of this vertex? So it has 2 incoming things. So 2 minus 1 is so we get 1 here. This one also has 2 incoming things, so 2 minus 1 is 1. And then at the end, the flow has to be conserved. So we have -2. Okay, so let's see. So now I have to count integer flows. Okay, so let's do that. So here is 0, so nothing can come out of net flow 0. But the next one is 1. This one is 1. So I have integers, so the only possibility is I put 1 here or I put 1 here, right? So if you put 1 here and 0 here, then in order to achieve net flow 1 here, this is forced to be 2. Okay, so that the net flow becomes 0, 1, 1, -2. Okay, and alternatively, this could be 1 and this could be 0. And then what does this have to be? This would have to be now nothing is incoming. So if I want to get 1, this better be 1. Okay, so and these are the only 2 possibilities. So the volume equals 2, and maybe you can tell that this polytope indeed has volume 2 because there's a simplex here and there's a simplex in the back. Yeah. Any questions? This result. Okay. So then we have this result. So now for the complete graph, the Chan Robbins Yuen polytope, its volume is the number of lattice points in the complete graph, but now the in degree is this 0, 0, 1, 2. So for example, for this complete graph, the net flow here would be 0. Here it would be 0. Here would be 1, 2, and -3. And so you see this pattern here in the complete graph. Okay. So it remains then to calculate this. Okay. And now you can appeal to that generating function Chris was asking me about to do that calculation. If you can extract that coefficient, in principle, you're done. Okay. So this equals some coefficient of x1 blah 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 of that product 1 minus xi xj inverse for every edge. You're in the complete graph, so you have every edge. Okay, so if you're able to calculate this coefficient, you're done. Okay. Any questions? So Zeilberger used that, and then he realized that to extract that coefficient, that's done by a constant term identity called the Morris identity that is related to the Zeilberger integral. So the Morris identity that he used says that the constant term of this rational function, but at least you maybe see it looks similar to that 1 minus xi xj inverse we saw before. If you extract the constant term of that, it's equal to this product of gamma functions. And remember that a gamma function is like a generalization of the factorial. For example, at integers n, you get n factorial here. So then Zeilberger said that when you take a, b, and c to be 1, this constant term is exactly calculating this. And then this product, when you evaluate a, b, and c equals 1, out comes the product of Catalan numbers. So, and that's the end of the proof. Okay. Any questions? So that's why it's not clear where the Catalan numbers come from, because they come from this kind of black box, this constant term identity. And Zeilberger's paper is actually just 1 page, and right now we're basically here. Okay, so I've been reading this paper really closely. It's only 1 page, but it just has a lot of interesting things. So so I started maybe looking at this next remark before the references to see what's to understand this. So let's maybe look at it. So so maybe here he says that there's some connection to Zeilberger integral, which is very interesting. But then there is this thing that conjecture 2. So it's follows in the same way. So so let's see what that conjecture 2 is about. Okay, and it says that somehow this is yeah. So let's see. So let's see that. So let's see what that is. Okay. So recall that when the volume equals the number of integer flows in the complete graph with this net flow, and this is the product of consecutive Catalan numbers. Okay. Sorry. Okay. So this conjecture 2 that was mentioned on that next line is another conjecture of Chan Robbins and Yuen that says that if you count the number of integer flows in the complete graph with net flow 0, 0, 1, 2, 3, and so on, but now you refine them by considering that there have to be k sync edges with 0 flow. You don't know which ones, but there's k of them that have 0 flow. If you do that, then it also has a product formula where the last Catalan number becomes this nn minus 1k. Let me tell you what that is. So that nn minus 1k is called the Narayana number, and it has this formula here, and it counts Catalan numbers by number of peaks. So for example, if you here are the 5 dig paths of size 3. So there's only one of them with 1 peak. There's 3 of them with 2 peaks, and there's just one of them with 1 peak, with 3 peaks. Sorry. Okay. So if you kind of consider that k sync edges have 0 flow, then you break the Catalan number into a Narayana number. So it's very nice. So he said, so somehow by another constant term identity, you can get that. Okay. And so here, for example, we have a geometric kind of volume object and a lattice point object equal to the Catalan numbers. And here we just have a lattice point count. So Carola Mezaros filled the gap and gave a collection of interior disjoint polytopes whose volumes have some equal to that. So that this refinement has both a lattice point and a geometric volume interpretation. Okay, so let's recall. So maybe so here we talked about how at mn 1, 1, 1 we get the volume of this cry polytope, and it's equal to these Catalan numbers. There is this refinement here where you there is this refinement here that gives you where you are able to break a Catalan the last Catalan number. Okay, and it has both a lattice point interpretation and a geometric interpretation. Okay, and yeah, I guess here this also is some constant partition function. Yeah, I'm sorry about all these K's kind of flying around and meaning different things. Yeah. Okay. So well, there's still two empty things here. So well, this Morris identity holds for not just a, b, and c equals 1, but it holds for integers. So what does this also? So the question is, does it also have some geometric interpretation, some lattice point interpretation? Okay, so here is again the Morris identity. So a and b are non-negative integers, and c is a positive integer, and it's equal to this product of gamma functions. Okay. So consider a complete graph, but now you're gonna have edges with different multiplicities. So you have a complete graph with 0 up to n plus 1 vertices, and all the dots are kind of internal vertices. Okay, so and 0 is a source and n plus 1 is a sink. So you're going to have each edge from the source to an internal vertex is going to appear A times. Any edge from an internal vertex to the sink is going to appear B times. And any internal edge is going to appear C times. Okay? So you have this kind of multi-complete graph. And Sylvie Corteel, Yang-Soo Kim, and Carola Machado showed that the volume of this kind of multi-complete graph is equal to the Morris identity. Okay, and they use that with that translation theorem of Poznikov, Stanley, Baldoni Vergne that tells you volume equals lattice points. Okay, so the whole Morris identity is a volume of an object. And okay, so now, well, from this diagram, the question is, well, can we refine? Is there a refinement of MNABC? So can you put a K somehow here too? And does it have a lattice point interpretation? So, and also a geometric interpretation. Okay, and that's what I'll answer for in the last 5 minutes. Okay, so okay. So I have 5 minutes, Eric. That is.
Yeah, I don't know what the official time. I mean, at least 5 minutes. I mean, I think speakers often go till 1 o'clock. So I mean,
okay, so
it can take a little longer than 5 minutes.
Okay, and this is what we do. So so let me give you a new constant term identity. So now I'm going to define. Thank you. I have this psi. So I have my ABC. I have n, and now I have k also. Okay, and this means constant term in the x's. And this means coefficient of t to the k. Okay. Okay. So just let's see that kind of all the pieces are there. I have C here, A and B here, and now the t here is here in this fashion. Okay. So I extract a constant term of a coefficient of t to the k. Okay. So this is how this is defined. Okay. Okay. A bit mysterious, and this was inspired by that line on this Zeilberger paper that said that we do something with Awamoto's extension, Awamoto's proof of the Zeilberger integral. So that was kind of the inspiration to try to do this. And the theorem with William Shi is that it has the following product formula, where you have the Morris identity and a bunch of other things. Okay. So when you A, B, and C equals 1, well, this we know becomes the product of Catalan numbers. And what's remaining actually becomes a Narayana number. So that maybe you can check. Okay, so it reduces to that case. And the proof uses several recurrences, and like I think 4. And this one is the really non-trivial one. So in particular, this implies the formula for MNABC. So in principle, it implies, it gives a new proof of the Morris identity also. So, but so I told you that, okay, the Catalan numbers have more than 200 interpretations, but so, well, anyways, but this is like the really non-trivial relation that if you could prove combinatorially, you would have the price, okay? And I'll talk more about that, but okay. But here is this relation where you're changing K, and that's kind of the interesting one. Okay. So that's how you get the product formula, but is this calculating something geometric? And that's what we're going to answer next. So remember that this Kn plus 2ABC was this multi-complete graph with A edges, B edges, and C edges. So now we have one more piece where we take a set S of 1 up to n, and we consider these graphs where you add n edges going from the source to the sink. But now, importantly, for anything in S, you're going to delete an edge from the source, and you're going to add an edge from the sink. So here, this example, S equals 1. So you take this vertex and you delete one of its A edges to the source, and you add an extra edge to the sink. Okay. So for this edge, it has A minus 1 and it has B plus 1 edges to the sink, and the rest is the same. Okay. So that's how you change the graph. And then our second result is that this constant term equals the sum of the volumes of all these polytopes, where you sum over all sets of size k. Okay, so the sum of all these n choose k polytopes, the volumes of these polytopes, equals that product formula. Okay, and when a and b and c are 1, you get Carola Mesaro's interpretation, geometric interpretation of, like, if you put all these together, you get Narayana times Catalan. And this kind of inspired the generalization, how to do generalization. Okay, so this is the result from before. Here's an example. So here we have just n equals 2. So I can either get, I have 4 sets. So here's the empty set, the complete set, the 1, 2, and then here are the 2 sets of size 1. So if you take the flow polytope of this, the volume of this plus the volume of this, you get this value. Okay, so you have to kind of put them together. Individually, they're not nice, but together they're nice. Okay, any questions? So let me tell you a little bit about the proof here. So the proof of this result uses the subdivision lemma of Postnikov-Stanley. So it gives a map that tells you how to subdivide a flow polytope into pieces that are also flow polytopes. So this lemma says the following: if you have a vertex I with an incoming edge and an outgoing edge, so here this has flow x and y. So you take your polytope, okay, and you subdivide it by the hyperplane x equals y. So there's 2 possibilities: either x is bigger than or equal y, or x is less than y. And if x is bigger than or equal y, that piece is a flow polytope of this graph G1, where you remove this edge and you add this edge, or you remove the incoming edge to I and you add this edge. And then somehow you can still recover all the flows, so you leave everything the same, and then this would be a y, and this would be x minus y, or this would be x, and this would be y minus x. Okay, so you can decompose the flow polytope like that. Okay, so it tells you that the flow polytope subdivides into the flow polytope of these 2 graphs. Okay, so we just do this. We apply this subdivision lemma once at each internal vertex, and that's how that result comes about. Okay, so it's part of the idea. So as a corollary, we get that the Morris identity is refined by these psi's. So if you add over all k from 0 to n, you get the Morris identity. Okay, so basically this is a volume of this kind of flow polytope of k, a, b plus 1, c, and if you subdivide this polytope into 2 to the n pieces, you can clump them in by size of that set, and you get that result. Okay. Okay, so our contribution was kind of filling this here, where we have a new refinement, and we have a geometric interpretation. We have first a product formula for this constant term. Okay, so this is some kind of constant term of some coefficient of blah blah blah. It has a product formula. It has a geometric interpretation as the volume of a bunch of polytopes put together. And it has, I didn't talk about that, but it also has a lattice point interpretation. Okay, and it gives a proof of the formula for M and ABC. That gamma function thing. Sorry. Okay. So at 1, it would, which at 1, it gives you the product of Catalan numbers. Okay. So that's what we did. But the big elephant in the room, well, what about that combinatorial proof? So where are these Catalan numbers coming from? Is the proof combinatorial? And not entirely, because this to prove this product formula, there is this non-trivial relation, and this one, the proof is not combinatorial, we have to use some symmetric functions. So the proof of this, proof of this relation, of this recurrence, is not combinatorial yet. So if you're able to show this combinatorially, in principle, you would have a combinatorial proof of the Zeilberger's result. Okay. So that's all what I have for today. So the paper with William is coming soon, and this is the paper with Carolina Benedetti, Chris Hanusa, Pamela Harris, and Simpson that has the connection to juggling sequences, and Anthony. Okay. So thank you very much.
All right, let's thank Alejandro for a great talk.
Any questions?
Are there questions?